All right, we're going to look at this problem right here where I've got two loads in parallel. All right, load 1 is absorbing an average power of 8 kilowatts at a leading power factor of 0.8, and load 2 absorbs 20 kVA at a lagging power factor of 0.6. So the first question I'm asked is determine the power factor of the two loads in parallel. Now, one thing that you might think is, well, if I've got two loads in parallel, maybe I want to figure out what their impedances are and figure out what the impedance of the two parallel loads is. That's not typically how we think in power systems. We usually don't think of impedances. These might be two buildings connected in parallel with each other, and it's much easier to have a power meter to measure the P and Q for those two buildings than it would be to actually know what all the impedances are in the buildings. All right, and so to do that, basically what I'm going to say is that I can add up powers around the circuit. So essentially what I have here is a voltage source Vs. I'll draw it explicitly as a voltage source. And then I have some impedance here, some impedance for load 1 here, and some impedance for load 2 here. All right, just to be clear, what we're going to say is that the apparent power given out by that source, all right, that apparent power is going to have to be the same as the apparent power into load 1 plus the apparent power into load 2 plus the apparent power in the line, which is this guy here. Okay, so in other words, the source is the only place from which all of that complex power can come. So what I can do is, when I'm asked here to determine the power factor of the two loads in parallel, what I need to do is to figure out S1 plus S2. Once I know that, I can combine those two guys and basically say I've got my voltage source Vs, I've got my line, and then I've got this combination of, so I guess I'll call this L1, L2 combined. All right, and these guys are represented by what I'll call S here, whereas this guy is S1 and this guy is S2. Okay, so in other words, S is the additive sum of S1 plus S2, and the total power coming out of the source is S line plus the power that goes to each one of those. Okay, and when I say power, in this case I mean the complex power. All right, so to do this, the first thing I really have to do is I have to figure out what is S1 and what is S2. So this is a very classic situation, what I call a power triangle problem. So what I've been given is two facts about load 1 and two facts about load 2. So the two facts that I'm given, for load 1, I'm told that it absorbs 8 kilowatts at a leading power factor of 0.8, and that load 2 has 20 kVA, which is its apparent power, at a lagging power factor of 0.6. Okay, so two facts about each one. So typically that's what we need. So I'm going to go to this here. All right, there's this typical process we follow when attacking these sorts of power triangle problems. Okay, when we look at these, the first step here is determine what quantities I am given. So typically, as I said, I need at least two of the following. Or typically what I have is two of the following. All right, so what I have is usually the apparent power. Remember the vector, right? So I'll jump to my summary slide here for a second. The vector is the complex power. The vector is the complex power, S. The real part of that is P. The imaginary part of that is Q. The magnitude of S, okay, the magnitude of S is what we determine to be called the apparent power, okay, and that guy has units of volt amps, okay. So I am typically given the reactive power, P, Q, power factor, some combination of those four things. I need at least two of them, and so typically I'm only given two of them. If I have two of them, then I can figure out all of them. All right, in other words, I can figure out everything I want. I can figure out everything I want about this sort of triangle between S, Q, and P. I can figure out everything I would want to know about that if I'm given at least two of these quantities. Now, the next step is to determine, because I want to be able to draw the power triangle. But to be able to draw it, I need to be able to determine if phi z, the angle of the impedance, which is also, remember, the angle of the complex power vector. If I want to determine whether that guy, if I want to draw this thing, I need to determine whether or not I draw S up or whether I draw S down. And whether I draw S up or S down depends on whether my load is capacitive or inductive. So we remembered, all right, this sort of basic summary here. If I have an inductive load, the impedance angle is positive, okay? Which means that my complex power vector would be up here in the first quadrant. If I had a capacitive load, my impedance angle would be negative and the S vector would be in the fourth quadrant. So the way this is termed typically is we say that our load is either lagging or leading. And the terminology comes from the fact that I is either lagging V or leading V. Okay? So just to remind ourselves, if I have, remember Ohm's law is V equals I Z, right? So think about this for a second. If I had a load that was inductive, so here's I, here's V, right? The impedance of an inductor is, because remember Z equals J omega L, that has an angle of 90 degrees. So I have 90 degrees plus angle I equals angle V. So I have that angle I is equal to the angle of the voltage minus 90 degrees. So in other words, I is 90 degrees behind the voltage, or I is lagging V. Okay, so the terminology we typically use for an inductive load is that it's lagging, and the terminology for a capacitive load is that it is leading. And that term, lagging or leading, refers to the relationship between the current and the voltage. Okay, so if my load is leading, meaning that I have a capacitive load, my angle of the impedance is negative. And if my load is lagging, meaning that I have an inductive type of load, then the angle of the impedance is positive. Once that's done, I use trigonometry to determine all of the remaining components of the complex power. Okay, so let's follow that process here. And let's go back to my problem. All right, so I first, to be able to solve A and determine the power factor of the loads in parallel, what I need to do here is I'm going to say I need to get S, which we defined as the sum of S1 plus S2. So to do this, I'm going to have to figure out S1 and S2 and then add them up to get S. So let's do load 1 and approach that as a power triangle problem. Okay? So I'm told for this guy that P1 is 8 kilowatts or 8,000 watts. And I'm told that the power factor is 0.8 leading. All right, so I'm told two of the things that I said I needed to be given. So I have two of them, so I'm almost good here with everything I need. Now the question is, I said my second step is to determine whether phi z is negative or positive. So in this case, looking back to my steps here, if the load is leading, then I'm capacitive and my angle is negative. All right, so because I have a leading load, my angle is negative. So I'm going to draw my triangle like so. I'm going to say, here's my P, here's S. Now I'm going to write this as the magnitude of S, because if I think of it as a triangle, then the length of that side would be the magnitude of S. And then my Q would be going down this way, okay? This here would be phi sub z. So just using trigonometry. Step 3, I said, is to just use trigonometry. So we're at step 3, right? Remember here that power factor is equal to, we said, cosine of phi z. Okay, and it is. Okay, the trick with this is if I think about a situation like this, here my s vector is pointing downward and my phi sub z is here. Okay, so this is my s vector. The problem with cosine is that if I look at the first quadrant and the fourth quadrant, cosine is positive for angles in the first quadrant and positive for angles in the fourth quadrant. So if I have a negative phi z like I have right here, the cosine of that guy is going to be positive. And that's why we add that leading or lagging indicator to tell us whether the angle is an angle with a cosine of 0.8 in the first quadrant or the fourth quadrant. By being told that the power factor is 0.8, we're told that we have an angle whose cosine is 0.8 and that angle is in the fourth quadrant. So that means that when I do this, I need to say that phi z equals negative cosine inverse of 0.8, the power factor. Now I put that negative there myself just because I know that this angle is going to be negative. Because if I just take the inverse cosine of 0.8, I'm going to get a result in the first quadrant. So I need to use my brain to know that I put a negative sign in there to get that answer. All right. So once I have that, I can simply say, if I want to get everything else here, I would say, well, Q, just from using trigonometry, right? Just looking at this, not looking at any of those formulas or anything like that. Just using trigonometry, I know that Q has to be the magnitude of S times the sine of phi sub z, okay? And the magnitude of S, in this case, again, just looking at this relationship, the magnitude of S is equal to P divided by the cosine of phi z. Now I could get that from my vector relationships or just looking at that triangle that I've got right there. So right now I have everything I need to be able to do this. This is P, and again, I guess I'm calling this P1. I should be calling this phi z1 since I have another load coming up. All right, so I'll call this magnitude S1, Q1, phi z1. Okay, so P1 divided by power factor 1. Okay, now to get the total complex power, I just say S1 as a vector equals P1 plus JQ1. Okay, and I wrote a MATLAB script to be able to do that for me. Okay, the MATLAB script that I wrote, I'm not going to go through this whole thing in excruciating detail, but I've defined here P1 is 8,000, so it's this block of stuff right here between lines 5 and 10. So P equals 8,000, my power factor is 0.8, phi z1 is negative a cosine power factor of 1. Remember in MATLAB, inverse cosine is called arc cosine, a cosine. And all of MATLAB's trig functions default into radians. So if I want to get that into degrees, I have to multiply by 180 over pi. So the magnitude of S1 is P1 divided by the power factor. My Q is the magnitude of S1 times the sine of that angle. Now again, note that I multiply by pi over 180 because my angle here is in is in degrees, right? I made my angle in degrees, so I'm putting it back into radians. And so my S1 is P1 plus JQ1. Okay. All right, so we could determine what those values are. We'll get the numbers here in a little bit. Now for load 2, on the other hand, load 2, we were told that the load absorbs 20 kVA at a lagging power factor of 0.6. So that step 1 is to determine what I'm given. So what am I given here in this case? Well, by being told that it's 20 kVA, I've been given that the apparent power is 20,000. And again, that's in volt amps. Remember, all of these things, apparent power, reactive power, real power, all have units of volts times amps. So we arbitrarily give them these units that are different just so that we know how to differentiate between them. Okay, so apparent power has the volt amp units. Reactive power is VARs, or volts amps reactive. Okay, So the other thing I'm told is really about the angle when I'm told that I have a power factor of 0.6 lagging. All right, and so I'll call that power factor 2. And so that means the cosine of phi z2 is equal to 0.6. Now again, the second step in our process was to then say, well, is this triangle that I want to draw, is it pointing down into the fourth quadrant or is it pointing into the first quadrant? Okay, so I'm told that my load is lagging. So if I go to here, I say, well, if my load is lagging or inductive, then phi z is positive. Okay, so that means I'm going to draw this guy up. Okay, so I have a P here, a Q here, and magnitude of S here. This guy is the thing I've been told is 20,000. And then phi z2 is here. So I'll call that P2, Q2, S2. Okay? So first thing I can do here is relatively straightforward, and I can figure out P2 by going magnitude of S2, right? The magnitude of S2 times the cosine of this angle would be P2. So I could say times cosine phi z, all right? And I'm given everything I need there. Then I also want to figure out what Q2 is, which means I need this relationship, again, just simply from trigonometry, right? The key thing is I don't need to remember any of those formulas if I just look at this thing as a triangle and know my trig. Okay, so to do this, I'm going to need to know what the angle is. In this case, I say phi z2 is simply cosine inverse of 0.6. I don't put a negative sign in here because by default, inverse cosine is going to give me the positive angle. Okay, only if I know that the triangle is pointing downward do I have to worry about arbitrarily adding in that negative sign. Okay, so I can put those equations into MATLAB, and I did that here in lines 12 through 17. Okay, here's the information I was given. I go through this process here calculating phi z2, and then essentially what I do is run through my calculations for P2 and Q2 and combine them. All right, so at this point I want to try to answer A, right? So to determine the power factor that loads in parallel, I said I wanted to add the complex power of load 1 to the complex power of load 2 and to figure out the total complex power. So that's what I'm doing here on line 19. I'm taking S1, which was for load 1, and then I'm adding that to S2, which was for load 2, and then here I am calculating the angle and the magnitude. Okay, the angle and the magnitude. So again, just by simply using MATLAB's angle function and the absolute value function. Certainly I could take the real part and imaginary part and use Pythagorean theorem to get the magnitude, and I could use the arctangent to get the angle, but I'm just going to use the built-in functions because it's a little bit easier. So I'm going to take this, evaluate this in MATLAB, and what do I have here? So my S vector is, put these next to each other. My S vector, which is S1 plus S2, is simply 20,000 plus J 10,000. Okay, and I'm given what the angles are here. So the abs, so S mag is about 22,000. 22,361, and that would be in volt amps. And phi z, the angle of that guy, if I calculate that, is 26.5651 degrees. So 26.5651. So the combined loads have a positive Q, so a positive angle, which means that the combined set of loads looks inductive. All right, I don't know what the R and L values are for this combined loads, but it looks primarily inductive because it has a positive angle. Now I was asked for the power factor of it, so I take the cosine of phi z and I multiply that by pi over 180 because again it's assumed that I have an angle in radians, and that works out to 0.8944. So my power factor for the combined loads is 0.8944. Sometimes we refer to that as 89.44%. Okay, so we've solved part A here. Now what we're asked to do is the apparent power required to supply the loads. So the total power basically coming out of this source, the magnitude of the current I sub s, and the average power lost in the transmission line. So right now we haven't been told anything about what V sub s is. So I don't know the voltage across these components. I know nothing about that. I do know over here, I've combined this. Remember, I've gotten this thing to be, now here's V sub s, which we don't know. We have this impedance here. And we know that we've combined the loads and represented them by their combined complex power S. And I am told the voltage across here. So I can go back to my relationships that I have. Right? So if I look at my summaries here, I am told that S, the complex power, right? Complex power is always related to V times I conjugate. And I know the complex power, I know the voltage across it, so I can simply solve for the current using that relationship. So I'm told that for part B, I have S equals V times I conjugate. All right, in this case, I believe it's called I sub S for the current coming out of the source. And I'm told specifically that the voltage has a magnitude of 250 with an angle of 0. So that says that S, which we know to be, in this case, 20 kilowatts plus J times 10 kVars, right? That's just taking this value over here, equals 250 times IS conjugate. All right, so the approach to this, if I want to figure out what IS is, pretty straightforward. I basically say, I look at my vector relationship, I say the magnitude of S is the magnitude of V times the magnitude of I sub S. So the magnitude of I sub S is just the magnitude of S divided by the magnitude of V. And I have everything I need for that. Right, here's the magnitude of S over here, and the magnitude of V is 250. Angle-wise, I say angle of S, which is the impedance angle, is equal to the angle of V minus the angle of I, right? So from this, I can say the angle of I needs to be what? It's going to need to be the angle of V minus the angle of Z, right? I'd bring phi I over here and then phi Z over there, and I would have solved for this, okay? In this case, that says that I have 0 degrees for my voltage, minus phi Z, right? So that becomes minus 26.5651 degrees. So notice something here real quick. My voltage has an angle of 0 degrees. That's sitting sort of right on the real axis. I is somewhere down here. So I is lagging V, right? I has a negative angle. It's behind V, which has a 0 angle. So we call that guy lagging, all right? And that's consistent with everything I have here. When I have a lagging situation, the current's behind voltage, the impedance angle is positive, and the Q is positive. Okay. All right. So we can do math to get the magnitude of I sub s. So I'm going to throw that into MATLAB here in a second. All right. Now, once I know I sub s, the other thing I was asked to figure out here is the apparent power supplied to the required from the supply to the loads, and the magnitude of the current. So we've got that, and then the average power lost in the transmission line. So let's say I want to figure out what is the power in this line right here. So I'm going to write it right here. I'm going to say that the complex power in that line is simply the power in this guy plus the reactive power in this guy. So I'm going to call that P line plus JQ line. Now in this case, easiest way to look at that, since I don't know the voltage across this guy. In other words, I know the voltage here is 250 volts, but I haven't been told anything about V sub S. So if I haven't been told anything about V sub S, the only way for me to be able to figure out what this loss in this line is somehow to use the current. So I go back to my relationships here, right? So I got these guys here for active power and reactive power. So if I know the voltage and the current, then I can use hopefully this relationship here and this relationship here, but I don't. I only know the current in this case. So that leads me to form 2 over here, where I know the magnitude of the current, and I know the real part of the impedance and the imaginary part of the impedance. So I'm going to say, and notice real quick, just too, before I move on from that, this looks pretty similar to what I would have in DC circuits, where over here I've got a V times an I, then I have an I squared times an R, because real of Z is an R, and then I have a V squared over an R. So the same sets of relationships that I have in DC circuits. All right, so the way I would do this is I would say that P line is the magnitude of IS squared times 0.05, which is the real part of that impedance, plus IS squared times the imaginary part of the impedance, which is 0.5, all of that times J. Okay, that's how I would get that. Now again, I'll throw that into MATLAB here in a second. Now the thing that I said back at the very beginning is the total power coming out of this source over here, V sub S, is the power going into the line plus the power going into this load plus the power going into this load. Now we said the load powers, we combine them into just one vector S. The source power is whatever that S is plus the power in the line, right? In other words, all the power leaving the source, some of it goes to the two loads and some of it goes to the line. And just by conservation of energy, those things all have to equal each other. Or I should say more appropriately, the sum of these things, they all need to add up to the source power, okay? All right, so to do this, I'm going to say that S source is equal to S1 plus S2, like this, plus S line. And I know that S1 plus S2 I've already called S. So I just take the result that I obtained here and add it to what I obtained here to get the total source power. All right, so MATLAB, that's the blocks that I have right here. So just moving over a little bit. So first thing I did was here in lines 23 to 24, right? I figured out the magnitude of the current by getting the magnitude of S and dividing by V, okay? I figured out the angle of the current by saying the angle of the voltage minus the angle of the impedance. And then P line, I mag squared times 0.05. Q line is I mag squared times 0.5. Right, there's me getting S line, put them together. Okay? All right, so if I do all that, evaluate that, I want to look real quick at a couple of things. So S sub S, all right, S sub S, the power out of the source, is equal to 20,400, all right, plus J times, what is that? That's 14,000. Okay, so 20,400 plus J, 14,000. So notice there's an extra 4,000 VARs, which is going into this guy, and there's an extra 400 watts here, which is going into the resistor. So when I say an extra 400 watts, well, remember the load only needed, the combination of the loads only needed 20,000 watts plus 10,000 VARs, but the source has to give me 20,400 and 14,000. So the source is having to give me more complex power than my load actually needs because of this sort of non-ideal line. All right, that's basically what this is saying. And if I wanted to get some of those quantities I was asked for, I can see from this P line has to be the extra 400 watts. And if I go in and I get what is the magnitude of I sub S, the magnitude of I sub S in this case, so I guess I mag is what I called it, is 89.4427. 89.4427 amps, like that. Okay. Now it's asked me for the apparent power required to supply the loads. Remember, the apparent power is the magnitude of SS, right? So I would need to calculate the magnitude of that, which isn't too hard. I'm not going to calculate it here. All right, so now I've given this last question here, which says, given that the frequency of the source is 60 hertz, compute the value of the capacitor that would need to be placed in parallel with the loads to make the resulting power factor of the combination unity. Okay, so what I'm being told here is, I'm going to move this out of the way, right? What I'm being told here is I want to add a capacitor right here in parallel with the loads. Now, because I have a capacitor, again, go back to my summary, all right? Because I have a capacitor here, its angle is negative, its Q is negative, right? Remember, capacitive stuff, capacitive Q is such that the complex power is in the fourth quadrant. So the complex power points downward. So my Q is negative. And if I have a pure capacitor, there's no P, it's all Q, right? So in this case, I would say that the complex power of the capacitor here is negative, I'm going to write it this way, negative magnitude QC, or just JQC, where I know that QC is a negative value, okay? So looking at this, I could say the combination for the loads, right? So I'll write it now, I guess it's S loads, is S1 plus S2. This is what we had before, minus J times magnitude of the Q capacitor. What we are being asked to do here, right? I'm basically said that if I want the combination of loads to get to be such that the power factor of this combination is unity, right? If the power factor needs to be unity, let's just think about that for a second. So if power factor is 1, that means that the cosine of phi z is 1. So that means that phi z needs to be 0 degrees. So that means P is pointing this way and S is pointing this way. So there is no Q. Okay? So what that means is I want no Q to be here. All right? So let's take a look at the situation. So in this case, now in part C, I'm saying I want S loads to be S, so which is the complex power of the combination I have right now, plus whatever the capacitor is giving me. So we say plus JQC, which I say is in this case, I'll write it out since I know what S is. It's S, which is just for the loads, was up here. All right, so I bring that down. So this is 20,000 plus J 10,000. All right. And then for my capacitor, I say plus J times QC, or I'll write it as negative magnitude Q sub C. Okay. So what that tells me here is that Q sub C needs to be negative 10,000. Okay. So there's two ways to approach this. In this case, because I'm placing it in parallel, right? I don't know what current needs to go through this capacitor, but I certainly know the voltage across it because it's in parallel with these loads. That voltage in this case is 250. So looking at my sort of summary of things, if I know the voltage across an impedance, I can do V squared over the impedance. Because I'm talking about reactive power, it's volts squared divided by the imaginary part of the impedance. So I have QC equals volts squared divided by the imaginary part of Z, which, remember, in this case for a capacitor, Z is 1 over J omega C, or negative 1 over omega C is the way we write that. So I can do it that way, or alternatively, so just to, I guess, play this out for a second, V squared over negative 1 over omega C. So the minus signs very clearly cancel each other. The other way I sometimes do this is I'll say the magnitude of Q sub C needs to be 10,000. And the magnitude is equal to V squared over the magnitude of the imaginary part of the impedance. Okay. The magnitude of the impedance of the capacitor is 1 over omega C. So notice here there's no minus signs at all. Here the minus signs ended up canceling each other. I like to do it this way because essentially I know in the end that I better not ever have a negative value of a capacitor when I'm solving this type of a problem. You never have a negative capacitor, you never have a negative inductor, you never have a negative resistor. And so I better make sure that my capacitance is positive. Okay, so that's why I've got those two different ways of doing this. So if I want to figure out the actual capacitor value in this case, I need to say that it is, I'll rearrange this guy to be V squared omega C. So C equals the 10,000 VARs that I need divided by volts squared times omega. Now I know that the volts in this case are 250, right? Because that's the voltage across the capacitor. Now we were told here that the frequency of the source is 60 Hertz. So that means my omega in this case is 2 pi 60, like that. Okay, and then I go to calculate. Right, so over here, back to my MATLAB. All right, so here's my relationships here. So Q cap is on line 34, and then my calculation for the capacitor is right there. And I'm gonna evaluate this guy real quick. And my MATLAB result tells me that my capacitor needs to be 424.41 microfarads. All right, so my C is 424.41 microfarads. So with this particular capacitor, what I have done now is I have said that I've got the following. S equal to S1 plus S2, right, points upward like this. What I'm doing is I'm saying, all right, well, now I have some capacitor that has some Q value, which is downward this much. so that the total summation of those two things is just simply P, like that. So I just simply turned it into a p-value. So my new S, I guess what I'll call S new, all right, is basically just the p-value that I had before. So it should be just 20,000. And we call that unity power factor because the angle of that guy is 0 degrees. That means that the voltage and the current flowing through that load are in phase with each other. So if I drew V and I, they would align with each other, which means the load must now look like a pure resistor. So basically I've turned this system here from the perspective of the utility. The original system that I've got now looks like 0.05 and the inductor and a pure resistor. I don't know what the value of that R is, but as far as the utility is concerned, the combination of L1, L2, and the capacitor now looks like a pure resistor. Okay? All right. So, with all of that said, I added one remaining question here that I threw in, which is what is V sub S? Because we weren't told that. So, what is V sub S? Well, we happen to know, or we need to recalculate now with that capacitor what I sub S is. But I can basically say, well, I know what S loads is over here. I know what this complex power is. I know what IS is, so I can figure out S line again like I did before. That's going to be magnitude of IS squared times 0.05 plus J times IS squared magnitude times 0.5. Right? So I can do that just like I did before. And then I can use that to figure out the total complex power coming out of the source. Remember, we've always said that the total complex power coming out of the source has to be the power in this line plus the power in this load plus the power in this load, now plus the power in the capacitor. Okay? So I'm going to calculate S source now, given that everything has changed. So in this case, we're going to say, well, if S new is 20,000, that has to be equal to voltage times IS conjugate. Okay, so in this case, I know that this is 250 angle 0 degrees, and this is IS magnitude times the angle of phi sub I. Okay. And I can figure out the magnitude of I sub S by doing 20,000 divided by 250. And if you do that calculation, that works out to be 80 amps. Okay. Now the angle here, let's just look at this. The angle here, the angle of S, which is the angle of phi sub Z, that is equal to 0 degrees in this case because I have unity power factor. That's equal to phi sub V minus phi sub I. That's just me looking at this relationship to say angle of this equals the angle of this minus the angle of this one because of the conjugate, right? So because the angle of the voltage is 0, the angle of the current here is also 0 degrees, right? So the current and the voltage are aligned with each other as we said they should be. All right, so I've got my current phasor. Then I need to figure out, well, S line is equal to 80 squared times 0.05, which is the resistance, plus J times 80 squared times 0.5, which is the imaginary part of the impedance here, right? And so I can say that S source new, now that I have this capacitor, is my S line, and I guess maybe I should call it S line new, plus S loads, or what I just called S new, I guess. All right. So I add this and this to get my total source. Now, once I have that total source, if I look at the circuit, here's VS, all right, and then my loads. So I'm told what I sub S is. I know what S sub S is. So if I want to figure out V sub S sub S, and in this case I'm just going to call it S sub S new because this is after I've added the capacitor, has to be Vs times Is conjugate. Okay, so the magnitude of the voltage that is required here is going to be the magnitude of SS new divided by the magnitude of I sub S, like that. I'm just looking at my vector relationship. And the angle of SS new is equal to the angle of VS minus the angle of I. And I know the angle of I in this case is 0 degrees, so right, this is 0. So the angle of the voltage source is the same as the angle of S new. So if I go to my MATLAB, all right, so I go to my script over here. All right, if I go to my script, all right, so here's where I calculate the magnitude of the current, right, by taking the magnitude of the complex power going to the loads and dividing by the voltage. I'm recalculating here what the loss is. I combine the loss and the complex power in the load. And then I go through the calculations that I just wrote here, right, to figure out the magnitude of the voltage and the angle of the voltage. Okay, so take all of that, evaluate it. What do I see? The angle of the voltage is positive, so phi sub Vs is 8.9495 degrees. And if I look at Vs magnitude, let's make sure that's the right value I chose. Forget what I called it. Yeah, Vs mag. Vs mag is 257. So the magnitude of Vs is 257.1303. So a couple of things to note about that, right? So in this case, the current is at 0 degrees. So here's I sub S. And the voltage V sub S is here. So V sub S, right, is leading I sub S, right? So we see this is a lagging condition because we define the term leading and lagging based on where the current is relative to the voltage. So the current, even though it's at 0 degrees here, is lagging that voltage. That makes sense because if I look at what's going on here now, when I did my power factor correction, I basically said with my power factor correction, I got rid of any reactive power that was going into these loads. So I made the combination of the loads look like a resistor. So I basically have a resistor for my loads, this 0.05 ohm resistor, and then this inductor here at 0.5 ohms. So there's a little bit of inductance in the overall circuit. So if there's inductance in the circuit, there better be a positive Q. So the impedance angle better be positive, which means that current better be lagging voltage, and it is. Okay, so that makes sense. I also see the magnitude of the voltage is 257, whereas the magnitude of the voltages across the load is 250. So in other words, the voltage at the source is about 7 volts bigger than the voltage at the loads, which also makes sense because there's some voltage drop as the current flows through that impedance. All right, that should help with your homework.